Right. Thank you everyone for your interest in this presentation. My name is Raimundo Ibaceta and I'm a PhD candidate at the University of New South Wales in Sydney. And in very simple words, I'm going to be talking today about how can we improve shoreline models predictions by allowing the model parameters to vary in time. So just as an introduction to put you in context, there's been increased attention in the last decade to develop and to improve shoreline change models, which are semi-empirical shoreline models or reduced complexity models where we normally fit our simple mathematical expression to our forcing and shoreline change time series by assuming constant parameters throughout the period of calibration. So to put you in context and into a bigger picture, I'm showing you here an example from adapted from a publication in 2017 from Splinter et al. So I'm showing you 8-year time series of shoreline change in the Gold Coast in Australia. So it's the principal characteristic of this data set is that during the first 4 years of the data, the shoreline had a seasonal behavior and then switched to a more storm-dominated behavior. So if we run a shoreline model during the first half of the data, we can see that a shoreline model can very well predict the seasonal behavior. But now if we use this calibrated model and its calibrated parameters to forecast the rest of the data set, we can see that the forecast, and it underestimates the erosion during the second period of time. However, if we now use the same model to predict again how the shoreline change can be predicted with this model, we can see that a different set of model parameters now predicts much better the erosive periods during the second half of the data. And the recent studies have sort of consensus and emerging thought that the quality of the forecasting and hindcasting is highly dependent on the selected calibration periods, and in particular on how the underlying wave climate is during that period. So as a motivation in the current context of climate variability, where we are expecting the future waves to change not only in magnitude, but also in terms of its storminess characteristic, we could argue that if we want to predict future shoreline variability, we would need to potentially adjust our model parameters into the future if we want to correctly predict shoreline change. So inspired by recent studies in the field of hydrology, we're going to apply a data assimilation technique called dual state parameter ensemble Kalman filter to track the time varying model parametrizations within an established shoreline model. So first we're going to apply the technique to synthetic cases to test the capabilities of the method, and then we're going to apply it to a real world scenario. So we're going to be using the generalized short-form model published in Splinter et al. 2014. So it's a very simple structure of model forced by the dimensionless fall velocity, an equilibrium term, and the wave power in shallow waters. So there's 4 model parameters. One of the parameters, which is the B term, we're not going to take it into account in the study as we are interested now only in the parameters associated with cross-shore processes. So the first 2 of them are the magnitude rate parameters, which simply dictate the efficiency of cross-shore processes. And the last one is the phi term, which is an indicative of the time scale of, or what are the time scales of shoreline response. So an important thing of this model is that after applying the generalized shore for across different beaches around the world, the Splinter et al. 2014 was able to parametrize these two parameters as a function of the interannual magnitude of the dimensionless fall velocity, or the average of its of the dimensionless fall velocity. So the magnitude rate parameter was parameterized using a monotonic expression as a function of the average of the dimensionless fall velocity, and the frequency response was parameterized as a function of the variability of this term. So this suggests that if for a single beach, the characteristics and the magnitude of the dimensionless fall velocity changes in time and in the future, we would have to potentially adjust our model parameters to correctly predict shoreline variability in the future. We first created 10 synthetic scenarios using the short-form model. We set different 20-year synthetic time series of wave climate, and we predefined 4 different shapes that potentially represent the variability of the model parameters responding to underlying changes in wave climate. So the first shape is a flat shape, then we created a linear negative trend, a sinusoidal shape, and a stepwise function. So for example, the most complex scenario, which is the scenario number 10, is shown here. So in the top panel, the dimensional result velocity was used to force the short-form model, along with this combination of parameters, and that resulted in this time series of shoreline variability. That was then subsampled, and we also added some noise to represent the current state-of-the-art of shoreline detection methods, for example, from in situ surveys up to more noisy satellite-derived shoreline. So this resulted in a total of 480 individual test cases to try the capabilities of our dual state parameter ensemble Kalman filter that in other literature has already been shown successful for tracking parameter changes. So going to the results in the synthetic cases, in this figure here from top to bottom, I'm showing you shoreline time series, the magnitude rate parameters CA and CE, and the phi term for the most complex scenario 10. And in black is the ensemble Kalman filter estimation, and in red, the true synthetic values. So we can see that even for the most complex case, the ensemble Kalman filter is able to estimate time varying parametrizations across the 20 years of data. We also tested how the Kalman filter skill changed as we increased the accuracy and the time sampling of our data. And in general, we found that for all of our cases, shorelines with noises, with levels of noises below or smaller than 7 meters and measure up to bi-weekly time samplings result in good tracking of the proposed changes in the parameters, not only in their magnitude, but also in the time scale that we are aiming to look. So now we're going to apply the method to the Gold Coast, Australia, in the same example that I conceptually explained to you in the introduction. So basically in the Gold Coast, there is an Argus camera, and we're going to be focusing on this area of the beach, which has minimal gradients in a long-shore sediment transport, which allowed us to use the short-form model, which is a cross-shore model. So we're going to be using weekly shorelines that have an accuracy of approximately 5 meters. So if you guys remember this, we're going to be using the same period that was characterized by a change in the nature of the shoreline behavior that switched from a seasonal behavior to a more storm-dominated behavior during the 8 years of the data. So in red line, I'm showing you what the short-form model can predict during the whole 8 years. And now we're going to compare that prediction with what the ensemble Kalman filter is able to do. So on the right figure, from top to bottom, I'm showing the shoreline time series, the magnitude rate parameters, and the phi parameter. And we also showed the B term, but we're not going to focus on it in this presentation. So in black is the ensemble Kalman filter estimation, and in red, the flat magnitude of the parameters derived from a global optimization technique in the classical or regular short-form model. So first of all, we can see that the ensemble Kalman filter is able to track time varying parameters. And this variability is tracked on multi-year time scales with some seasonal responses that are also out of the scope of his work. And most importantly, the ensemble Kalman filter is able to improve the model predictions, for example, shown in these erosive periods here, because of the now time varying parameters. So now this offers the opportunity to potentially link these parameter changes to the non-stationary in the underlying wave climate during this period of time. So we're going to focus only on the parameters that the Splinter et al. Was able to parameterize. So if we focus first on the CA parameter, and we remind that this parameter was parameterized as a monotonic relationship between the magnitude of the parameter and the average of the dimensionless full velocity, we can see that for our case, increasing periods of this parameter matched with decreasing periods of the average and dimensionless full velocity in a random basis. In a similar way, periods where this parameter was decreasing also matched with periods where the dimensionless full velocity was increasing, in line with the parametrizations of Splinter et al. 2014. Now, if we switch to the phi term, and if we remind that this parameter was parameterized as a function of the variability of the dimensionless full velocity, and if we also remind that Splinter et al. Was able to define a sum where this parameter could switch in magnitude from a seasonal to storm response, we can see that our ensemble Kalman filter, in fact, tracked first a period where the parameter remained fairly constant during this seasonal characteristic of the waves and shorelines, and then it deviated twice towards lower magnitudes that represent more storm-dominated response. Now, if we quickly see what the significant wave height, and we track these storms during the whole 8 years, we can see that these two periods were characterized with years where the storms occurred throughout all the year and not only during the first half of the data, as it is more common in a seasonal response. So just as a summary and outlook, our ensemble Kalman filter was able to track non-stationary parameters, and the application to a real data set shows that we can potentially link the time-varying parameters in an empirical basis to the underlying changes in wave climate. And the current work that we're doing is applying this to future data sets to train model parameters for future forecasting. So in this conceptual figure shown here, if now I apply my ensemble Kalman filter and during the first part of the data or the training period, I'm going to be able to potentially derive time-varying parametrizations that I'm going to be hopefully empirically relating to the waves. And now we could use with more confidence these changed parameters to obtain a more confident forecast as a function of the changing wave climate. That's all for me. Thank you.